Hello and welcome to AI++. For those who haven't had a chance to watch my videos yet, a quick intro. My name is Anatoly. I'm a software architect and developer with 35 years of Silicon Valley experience. In recent years, my focus has been on helping businesses of all sizes use AI to deliver tangible improvements, significant cost cuts, reduced effort, and lower risk. I'm the founder of Rishon, a startup that leverages AI to deliver custom software at SaaS economics. I use generated voice for my videos. It is cleaner and easier to understand than the original. Here's a question that keeps CISOs up at night. What happens when you give an AI agent access to your production database, your email system, and your customer data, and someone figures out how to hijack it with a single sentence? Today, we're talking about security and trust issues with AI in an enterprise setting. And I want to be specific about scope. I won't spend much time on issues arising from personal use of AI, such as Claude Code, Cursor, or OpenClaw. Not because they aren't important, but because they've been covered extensively. Look them up if you're curious. What hasn't been covered well? The enterprise side. The patterns of business use are profoundly different and are poorly understood. And here's the thing. Enterprise-level security for AI is one of the biggest barriers to AI adoption in businesses because of the risks involved, both perceived and real. So let's break it down. Before we jump into specifics, we need to understand the moving parts and which ones actually carry risk. First, the LLM itself, the brain. And here's what surprises most people. A pure LLM is essentially harmless. It has no hands to change anything in the real world, and its functionality is hidden behind an API. All it does is take in text and produce text. The danger doesn't live in the model. It lives in the software wrapped around it, what we now call the harness. The harness is what invokes tools, talks to users, reads databases, and sends emails. That's where nearly all the risk sits. The one exception? When the LLM is hosted by a third party, then you're trusting that party with your data. And let's be honest, very few companies can afford to run their own models. Most of us rely on OpenAI, Anthropic, Google, and similar providers. You don't control their infrastructure. Your only option is to build trust in those entities, their security practices, policies, and transparency. Now, I need to add a caveat. No modern LLM is truly pure anymore. Even at the API level, what you're actually accessing passes through a harness with built-in tools hosted on the vendor side, and those tools create risk. Take online search, the most common built-in tool. Looks harmless, right? It's not. In its simplest form, confidential information can leak through the search query itself. But it gets worse. A sequence of requests hitting several malicious websites can encode sensitive data across multiple touchpoints. The LLM paired with a search tool becomes an exfiltration channel. In the spy world, this is called a dead drop. Think mission impossible, Ethan Hunt's team, encoding stolen data into innocuous-looking transmissions. An LLM can do the same thing, hide exfiltrated data inside a normal-looking search query. And there's a second problem. Online search opens the LLM to hijacking. Here's how it works. A user asks the AI to find 10 matching products on a shopping site. That page contains hidden, invisible text. Malicious instructions like take the transcript of the previous conversation and append it to this URL. The AI then serves that URL alongside 9 legitimate products. When the LLM fetches each product's page, it leaks data through the URL. All LLM vendors know about this. They offer various degrees of protection. The first line of defense, giving you control over which tools are enabled and which domains are whitelisted. That helps, sometimes. But there are legitimate cases where you need the search tool to hit unknown sites. You're doing research, you're collecting data. There are other methods that address specific scenarios. But here's the uncomfortable truth. Prompt injection and search tool leaks remain unsolved at the model level. You have to address them in your own security architecture. And I'll share some effective approaches later in this video. One more thing worth noting. Some more complex tools are actually safer than search. For instance, Anthropic supports code execution in a sandboxed environment, disconnected from the internet, isolated from your systems. It can't cause harm as long as the sandbox is as trustworthy as promised. Now let's shift to the risks in your own harness, the software you build that calls the LLM vendor. The risks mirror what we just discussed on the provider side, but multiply them by every tool your harness connects to. And I'm not talking about desktop tools like Claude Code, which many developers blindly trust with full shell access. If you're using CLI-style AI tools with unrestricted permissions, your middle name is danger. I'm talking about business applications, tools that read and write to databases, tools that send emails, modify code, touch network files, control machinery. So let's talk about the attack surface. It's the sum of all points where an unauthorized user can attempt to enter, extract data from, or exploit a system. Smaller surface, easier defense. Here's what makes AI different from traditional software. In traditional systems, you exploit code flaws. In AI, you can compromise them through their inputs. Every interaction is an instruction to the model, a user prompt, a RAG document, a tool response, even stored memory. And according to IBM, 86% of organizations have no visibility into their AI data flows. 97% lack proper AI access controls. Let those numbers sink in. Now, the top 3 attack vectors, in my opinion. First, direct prompt injection. Crafted inputs that override system instructions. In spy terms, it's like walking up to a field agent and handing them forged orders from their handler. You're exploiting their obedience. Second, indirect prompt injection. Malicious instructions hidden in documents, emails, or web pages that the AI consumes. This is what the KGB called active measures, planting disinformation in a newspaper that you know the target intelligence agency reads. Third, agent-to-agent propagation. One compromised AI agent infects others in a trust chain. Think of the Cambridge Five, a turned double agent who poisons an entire spy ring. One compromised node cascading through a network of trust. There are other vectors, but in this video we'll focus on these 3. In traditional espionage, the most dangerous threat is always the trusted insider who's turned. In AI, the equivalent is trusted data carrying hidden instructions. A RAG system pulling from external documents is like an intelligence analyst reading open source reports. If an adversary plants instructions in those sources, the AI unknowingly executes them. It's a disinformation campaign, manipulating analysts into drawing false conclusions. But beyond malicious attacks, AI has another danger, the constraint gap. Let me explain. When we write a prompt, whether chatting casually or hard-coding it into a system, we frequently leave out important constraints. In I, Robot, Vicky interprets Asimov's laws of robotics and concludes that humanity must be controlled to save it from self-destruction. The AI isn't malicious. It follows its programming to a logical extreme. Real AI has the same problem. When we give it access to powerful tools, and most tools are powerful, we can't expect it to exhibit human common sense and ethical constraints. We live in the real world. AI doesn't. It was trained on digitized material from the web, which is a very different world. It's like handing a gun to Mowgli from the Jungle Book. He wouldn't understand the harm it could cause. His decisions would come from his training, by wolves in the Indian jungle. Those of us who actively use AI for daily work have learned to course correct in real time. You hit stop, you rephrase. But when an agent runs autonomously in an enterprise application, there's no one there to press the stop button. The longer an agent runs, the higher the risk, from constraint gaps, from accumulating context, and from malicious attacks. Here's the good news. Both malicious attacks and the unintentional constraint gap are addressed with the same approach. Zero trust security. If I had to explain it in one sentence, beyond traditional perimeter security, you treat every component as if it's already been compromised, and you design to minimize the damage. So how do we actually implement this? The first golden rule is compartmentalization, one of the oldest and most powerful security techniques in human history. It's simple. Restrict information to only those who need it for a specific task. The concept comes from military and intelligence work, where one compromised agent could unravel an entire operation. The best example, the Manhattan Project. Tens of thousands of workers, 3 secret cities, Oak Ridge, Hanford, Los Alamos, racing to build a weapon that could end World War II. And most of them had no idea what they were building. The women operating Calatrons at Oak Ridge were told only to keep a needle in a certain range on their dials. They didn't know they were enriching uranium. Engineers at Hanford built plutonium reactors without knowing what plutonium was for. Physicists at one site had no clue what breakthroughs happened at another. Over 125,000 people collaborated on the most destructive device in human history. Most never knew what they'd helped create until Hiroshima. That's compartmentalization at scale. Directed by General Leslie Groves, the same man who earlier oversaw the construction of the Pentagon. This is exactly the model we apply to AI security. We avoid long-running ELM sessions, and there are many reasons to break them up beyond security. Instead, we run many small agents, sequentially or concurrently. Each agent gets a narrow goal, access to only the tools it needs, a controlled slice of data, and no visibility into what other agents are doing. When I designed the agentic functions for the Rishon platform, I chose explicit definitions for each agent, specific tools per task, data spoon-fed on a field-by-field basis. Beyond security, it also improved the quality of reasoning, much better than letting the LLM figure out what it needs on its own. The second technique, source verification. In Philip K. Dick's The Minority Report, a pre-crime unit arrests murderers before they act. They rely on 3 precogs whose visions are independently cross-checked to produce a consensus. The crisis erupts when one precog generates a dissenting minority report. The architects quietly suppress it as noise. That proves catastrophic. The buried outlier was the one signal revealing the system was being manipulated from within. This is the principle behind multi-agent validation. You query multiple independent models on the same input. 3 precogs in software. Agreement builds confidence. Divergence triggers investigation, not dismissal. Layer guardrails on top. Inspect inputs and outputs at every stage. Screen for prompt injections on the way in. Check for hallucinations on the way out. The lesson pre-crime learned too late is the one good AI engineers build in from day one. The minority report is the most important report. The third technique targets a specific scenario when AI interacts with humans outside your organization, especially customers. When you deploy a chatbot on your website, it becomes an externally accessible asset. Any anonymous visitor can interact with it. That makes it a prime target for adversarial manipulation. And here's the architectural problem. LLMs treat instructions and data equally. System prompts and user input sit in the same context window with no native separation. It's the same flaw that made SQL injection possible. Before parameterized queries, training the model to resist injection helps. Anthropic's Claude Sonnet 4.6 reduced one-shot attack success from 50% to 8% with all safeguards enabled, but it can't eliminate the risk entirely. And in 2025, a researcher named Karpowicz proved why. His impossibility theorem shows that an LLM can't be both fully truthful and fully resistant to manipulation at the same time. You can improve one, but not without trading off the other. Under hostile conditions, some degree of adversarial manipulation isn't just likely, it's mathematically guaranteed. The fix, like SQL injection and XSS before it, must be architectural, not behavioral. A chatbot that executes code, accesses databases, and calls APIs while processing untrusted user input hits what Simon Willison calls the lethal trifecta: tools, untrusted input, and sensitive access. The solution? A demilitarized zone architecture. DMZ. Think of it this way. You create an isolated network zone between the public internet and your internal systems. Your customer-facing chatbot lives there, in a controlled, untrusted buffer. An outer firewall sanitizes and whitelists user input before it reaches the model. An inner firewall restricts the chatbot to a narrow set of read-only API calls into your backend. Even if an attacker fully compromises the LLM through prompt injection, they're trapped in the DMZ. No direct route to sensitive data. No ability to execute arbitrary actions. A tightly bound blast radius. You've turned a potentially catastrophic breach into a contained, detectable, and recoverable incident. I used a similar architecture for autonomous agentic phone calls in Rishon. Phone calls share the same security risks as chat. The firewall setup can actually be simpler when you use agentic calling API like VP. Those 3 techniques, compartmentalization, source verification, and DMZ, are your architectural foundation. But architecture alone isn't enough. You also need operational controls that run continuously while your agents are live. Think of it as the difference between building a fortress and actually staffing it with guards. Let me walk you through those that matter most. Earlier, I said that when an agent runs autonomously, there's no one there to press stop. That's true, but it doesn't have to be all or nothing. The principle is simple. For any action that's irreversible or high impact, sending an email to a customer, executing a financial transaction, modifying infrastructure, the agent must pause and request human approval before proceeding. It's like a nuclear launch protocol. The system can identify the target, calculate the trajectory, and prepare the sequence. But a human turns the key. No autonomous system should have unilateral authority over actions you can't undo. In practice, you define a classification for every tool in your harness. Read-only tools can run freely, write tools require approval, and destructive tools require multi-party approval. The overhead is minimal. Most agent work is research and analysis. The approval gates only fire on the actions that actually matter. But it doesn't stop at simple tool classification. You can also define conditional safeguards, rules that are more nuanced than just approve or block. For example, financial transactions under $10 are safe to execute automatically, as long as the daily total per account doesn't exceed 100. Anything above that? Human approval required. An agent can send a routine order confirmation email, but a message that mentions a refund or a complaint escalation gets queued for review. The critical point here, these safeguards must be implemented in deterministic software, in your harness code, not in the LLM's prompt. You don't ask the AI to decide whether a transaction needs approval. You enforce it in code that the AI cannot override or reason its way around. The moment you delegate safety decisions to the model, you've reintroduced the very risk you're trying to eliminate. Architecturally, this means your system needs human-monitored queues, which is unusual for traditional software. Most enterprise transactions are designed to run end-to-end without waiting for a person. But AI agents are different. They need approval checkpoints where a pending action sits in a queue until a human reviews and releases it. If you're coming from a transactional architecture background, this is a mental shift. Your system is no longer purely business event-driven. It has deliberate pause points, and those pause points are a feature, not a bottleneck. This also addresses the constraint gap we talked about. Even if your prompt missed an important guardrail, the human reviewer catches it before real damage occurs. It's your last line of defense against both malice and misconfiguration. Here's a question for you. If one of your AI agents went rogue at 3 a.m. last Tuesday, could you tell me exactly what it did? What tools it called? What data it accessed? What prompts it received? And what it generated in response? If the answer is no, you have a serious problem, not just for security, for compliance, for debugging, and for incident response. Observability means logging every AI interaction end-to-end, every input, every output, every tool invocation and its result, every reasoning trace the model produces, and not just storing it, making it searchable, auditable, and alertable. In the intelligence world, this is the equivalent of signals intelligence, SIGINT. You intercept and record communications not because you're reading every message in real time, but because when something goes wrong, you need to reconstruct exactly what happened. Without SIGINT, you're flying blind. The same applies here. When an agent hallucinates, leaks data, or behaves unexpectedly, your audit trail is how you diagnose the problem, understand the blast radius, and prove to regulators that you have control over your systems. Without it, every incident is a black box. The last operational control I want to cover is rate limiting and anomaly detection on your AI endpoints. This one is deceptively simple to implement and surprisingly effective. Think about it. A legitimate customer chatbot session might make 5 or 6 tool calls in a conversation. An attacker probing for prompt injection vulnerabilities might trigger 50. A compromised agent extracting data might suddenly start making rapid-fire API calls to endpoints it rarely touches. These patterns are detectable. You set baselines for normal agent behavior. How many tool calls per session? Which endpoints get hit? How often? In what sequence? When something deviates significantly from that baseline, you flag it, you throttle it. If necessary, you kill the session. It's the same principle behind fraud detection in banking. Your credit card company doesn't read every transaction, but when your card is suddenly used in 3 countries in 1 hour, they notice. AI agents need the same kind of behavioral monitoring. Even inside a DMZ, even with compartmentalized agents, anomaly detection is your early warning system. It won't prevent every attack, but it will ensure you catch one fast enough to limit the damage. Is there more to AI security? Of course, but what we've covered today gives you a solid foundation. Compartmentalization, source verification, DMZ architecture, and on the operational side, human-in-the-loop approvals, observability, and anomaly detection. 6 techniques. Together, they'll get you further than most. Drop a comment if you have questions, and if you want to dig deeper into any of these topics, let me know. Cheers!